Good afternoon, everyone, and welcome to today's webinar on feeder protection and theory on the G multi-lane feeder protection relay setup. My name is Eduardo Iglesias. I'm currently the Senior Regional Manager for the Industrial Market in the Southeast U.S. And on behalf of the GE Grid Automation team here present, I would like to thank you for taking the time to participate in today's session. Before we begin, I would like just to take a couple of minutes to go over some housekeeping items. First, I want to make you aware that this session is being recorded, and as such, the video will be available for you for the next 90 or so calendar days for on-demand viewing. Okay, the recording can be accessed using the same link that you use today to access this live event. And the Teams platform that we're using has muted all of your microphones. So please use the chat box to communicate with us, ask questions. That chat box is either on the top right-hand corner of your screen or at the bottom center. It's the one that has the little question mark for you guys that are not familiar with the Teams platform yet. And we will email you a copy of this presentation tomorrow, so you have it for your records and future reference if you desire so. And if you need a copy of the certificate, please email Team Fahey or myself, and we'll make sure that you guys get it soon thereafter. Today's webinar, we have two of our technical application engineers, Mike Ramalashan, which will be our main presenter, and Paul Smith, which will be backing him up with questions and answers and that sort of stuff. So with that said, Mike, the floor is all yours.
Thank you, Eduardo. Good afternoon, everybody, and welcome to G Multilin's Feeder Protection Seminar. As Eduardo said, some housekeeping, just a reminder, please ask questions. There's a Q&A chat box, ask questions in the chat box. And Paul will answer them, and I will also answer the questions in the last about 15-20 minutes of the presentation. So before we jump right into the presentations, a brief review of our power system components and what components we're going to be focusing on in today's seminar. So first of all, everything gets started at the generating station. Obviously, this is where we generate, we convert, whether it's converting fossil fuel to energy, to renewables, wind, solar, convert it to using a generator, converting it to power. Then we use our transmission system to reduce the losses that when we transmit that power. To reduce the losses, we step it up to high voltages because of I squared T losses. So if we step up our voltages, we decrease our current, so we decrease the I squared portion of the loss calculation. Then finally, it gets stepped back down into, when it gets close to our load, into what we refer to our distribution stations, which then gets stepped down further to then travel to where the power is needed, whether it's an industrial facility, commercial facility, or obviously residential. The distribution substation lines distribute that power to our end users, and then at the, for example, at residential, then it gets stepped down even further to 120, 240, depending on the type of residential. And for commercial, you might have high tension, some high tension, so maybe at 4 kV, 13 kV, and industrial even higher, which will then have internal transformers to step the voltage down to the usable voltage range. In terms of residential, most of voltage we use is 120 to 40, and this is usually a single phase service. There are some special, like New York City, where they have underground secondary networks. You actually get a 3-phase service, so it's a 208 service instead of a 120 service or 240 service. So most of what we're going to be focusing on today is feeder protection on our distribution system. And we'll talk why feeder protection or overcurrent protection is most used on this distribution system. And typically voltages, when we talk about distribution system, here in North America, it's about 2.4 kV to 33 kV, 34 kV. Obviously, things are usually relative. I've had the opportunity to go to Bermuda, and their transmission voltage is actually 33 kV. So everything's relative. So then these radial lines or distribution feeders are tapped, whether overhead or underground. They're tapped into our loads. So for overhead, you might have a pole running through your street, and then you'll see a transformer at that pole, which then steps that 2.4 kV to 33 kV down to the 122 to 40 volt that we then use in our houses. For underground, you might see pad mount transformers instead of overhead pole top transformers. You might see them in your front yard somewhere. So just schematically how everything operates. Obviously, there are multiple distribution lines that go to multiple locations, to multiple load pockets. So every distribution line will leave the substation and via a breaker. So you have a circuit breaker at the substation. Then as it gets out into the distribution world, then you might have overhead reclosers, and we'll talk about what the purpose of reclosers are later on. Or as it goes even further, you might have fuses. The basic purpose of the circuit breaker, the auto recloser, and the fuse that we'll talk about is to interrupt or isolate parts of the distribution system when there is an abnormal operating condition in the distribution system. And there's a number of different abnormal operating conditions they can operate off, but most common that we think about the most is short circuits, right? Whether it's a face-to-ground fault, three-phase fault, face-to-face fault. And the beauty of the distribution system is mostly, and not all the time, is there's usually one source, where it's usually from the utility substation. There might be cases internally in some facilities that might have cogen, and that's a different scenario. And that's why we can apply overcurrent protection, because overcurrent protection inherently is non-directional by nature, and because most of our distribution system is only flowing in current, or power is only flowing in one direction, it's easy to apply overcurrent protection. So then the problem might come in when we're talking about parallel lines. If we have multiple sources, that will have a problem for us, whereas when we have a fault in one feeder, short circuit current might flow on two feeders. So that's the problem of having multiple sources, and that's in a transmission system that happens all the time, because every substation is a source, every connection on the transmission side is a source. So on a transmission end, we use different types of protection. Overcurrent protection by itself does not cut it. We need to use distance protection, we use differential protection and such to be able to overcome the issues of current being able to flow in all directions. So this is what I mean with, for an example, for a multi-source system. So for example, you have a generator within this 13.8 kV, say an industrial facility. So we have a utility feed comes in, and then we also have a generator, a cogen, or something to supplement the power that is being imported by the utility. Usually in normal conditions, the flow is towards the load. However, if you have a fault on feeder 1, for example, the generator at the industrial facility will feed fault current into that feeder. And so instead of having load flowing to power flowing towards the load, power is now going to flow back into the utility feeder, and we need to protect against that also. So distribution system, as the entire power system, we are fortunate in the fact that our power system, we are so good at what we do. Most of the time, people are with power. There are minimum outages, so a lot of people don't realize what goes on behind the scenes, what equipment is involved, how we work to keep that and maintain that, the power system up and running. Obviously, there are cases when a few times it does happen, like during natural events and such, that we do have outages, and then when people do have outages, that's when we, have to do things beyond that we normally do to get them back. But most of the time, the power system is fairly self-sustaining, pretty reliable, depending on the type of system that we have, and we'll talk about how we keep it reliable and how we guard against disturbances in the system from preventing outages, or at least minimizing outages. So some of the equipment, you guys are probably familiar with a lot of these pieces of equipment that we generally use in the distribution station system. So the fuses we talked about, so you might have a branch circuit of fuses that's protecting that branch circuit. You might have capacitor banks for voltage stability, right? So if you have a long feeder that is going from the substation to some rural area, because of the voltage drop across that long feed, the end user might see low voltage. So you might need to supplement that by adding capacitor banks to maintain that voltage stability. And we have the Artery reclosers. We'll talk, they could be pole top, they could be pan mount. Voltage regulators, similar to a capacitor, but it's more of an active way of maintaining voltage. Then we have sectionalizers or switches, which help us to isolate parts of the power system. So if we have a disturbance within a certain part of the power system, we can isolate that from the rest of the system, work on it, get it back in service, so that only the customers that are affected are in that circuit, so that all the other customers are unaffected by that disturbance. So when we talk about feeder protection, there are a number of different guidelines. I'm going to focus, most of our discussion today is going to be focused on the IEEE guidelines, and specifically the standard C37.230, 2007 version. It's the guide for protective relay application to distribution lines. And I've highlighted the sections that we're going to be focusing on mostly, which is obviously going through some of the fundamentals, which we've talked a little bit about. The fundamentals are understanding how the power system operates, understanding the components that go into the power system, and how the load flows and what are the fault characteristics. And then a lot what we're going to talk about is part 5 and 6, which is, the various components in the power system and what those various components do. And then obviously the nuts and bolts of what we want to discuss is how do we protect our distribution system with overcurrent protection or feeder overcurrent protection. So what are the nature of faults? How do faults happen in the power system? There are various types of faults. Obviously, the most common, probably 90%, 80 to 90% of the faults that we see in our power system are going to somehow involve ground, and specifically phase to ground or single phase to ground. So that's going to be the majority of the faults that we have in our power system. Everybody probably knows that already. But we also have to guard against phase-to-phase faults, 2 phase-to-ground faults, and 3-phase faults. The big difference between the 3-phase faults and the other types of faults are the 3-phase faults is a balance fault, so that's almost how the power system is normally operating, balance, but with high currents. And then the other types of faults are we refer to as unbalanced faults. So what happens when a short circuit happens? So we basically bypass the resistance to the load, right? So once we've bypassed the resistance to the load, we go back to Ohm's law, we decrease the resistance to the source. So we've done that, our current will increase. So it causes high currents to flow in our power system. That high currents, going back to the I squared R heating in our cables and wires, that can cause not only the wires, but in transformers and equipment and breakers and buses. It will start to cause the equipment to heat up. All of these equipment are built or designed to handle a certain amount of heating for short periods of time. So heating by itself should not have an adverse effect on equipment in real time. I mean, it will have an adverse effect in the long term, but that fault by itself at that moment in time should not cause an adverse effect in equipment. It'll heat up. And however, we need our relays or protective relays or overcurrent relays that we're going to talk about to be able to identify that fault and isolate that fault quickly, because if we don't, then once we let that I squared R go on for beyond certain time, it will cause permanent damage to the equipment. So that is the consequences of having short circuit is it's going to cause high currents in our power system, it's going to cause heating in our power system, and eventually, if it's not cleared, it's going to cause permanent damage to the equipment, transformers, buses, and such. It's not a bad thing that the currents are high during fault situations, because that's as how a protective relay determines there's a fault. Because normally the current is low in the load region, and then suddenly increases very high into the fault region, and that's how the relay will tell there is a fault on the power system. That's its methodology of determining there's a disturbance in the power system. Short circuit is bad for the equipment if left for long periods of time, if it's not clear. However, it's also good to have high currents, so we can have relays that can sense short circuits on the power system. What are some of the causes of power system short circuits or faults? Obviously, natural events like lightning, wind, ice, and snowstorms. I used to work for a utility in Con Ed in New York City, so I dealt with a lot of ice and snowstorms. But now I've moved into the south. I'm in Orlando, and now I deal more with lightning and wind. So it's kind of two different ends of the spectrum. So it's kind of interesting to me to see, what are the things that a utility has to take into consideration when they're designing their power system. Obviously, contact by animals, aging. We have a very old power system, and not all the time we upgrade it when it's gets to the end of the life. We actually probably running it beyond the end of its life. So a lot of it is aging. Aging will have issues where they will be more susceptible to permanent damage. Human error, believe it or not, human error is the big cause of some of these faults. That somebody forgot a ground on a feeder, somebody forgot to lock out or tag out some piece of equipment, and they close it in, causes a fault on the power system. I remember a while back, I think in Florida, at the time I was living in New York City, there was an incident where somebody actually forgot to put the protective relay back in service after testing. And when they energized the equipment, there was a fault, and the protection system was not able to clear that fault, and it caused a widespread outage because also the backup protection had to operate. There are what we refer to permanent faults and temporary faults. So temporary faults we'll refer to them as transient faults because they're transient in nature, they're not permanent, they come and they go. Some examples of that are lightning, right? Lightning striking a conductor, whether it goes to ground, where it goes face to face. In this picture, showing a lightning strike that goes across the two phases. But the lightning strike is temporary in nature, right? So eventually that fault is not permanent. That short circuit is not permanent. Now, if you have a wind blowing two conductors together, if you have a conductor that's really old and it's sagged over the years, you can blow it, the phases together. Tree limbs, if they're not trimmed properly, they can, on a windy day, they can blow and make contact with a conductor. Then there's some permanent faults, which are faults that are not transient, and when they happen, we have to go out there and fix them. You know, we have to replace the equipment, we have to replace the, whether it's a dumb conductor, we have to replace the conductor, whether it's like a breaker that's has arcing on it, a permanent arcing on it, and then that's caused the breaker to fail, then you need to go up and replace that piece of equipment. Let's talk about system grounding. I don't know if you've attended the generator seminar a couple of weeks ago that we did. We talked about generator grounding, and one of the things when we talked about grounding methodology is grounding methodology depends on the type of protection that you use, or the type of protection that you need to apply. So it's prudent for us to talk about some of the grounding methods that we use in our distribution system, so that we understand the type of protection that needs to be applied for those various methods. So grounding, why does it need to be looked at? As I mentioned, it depends on the type of protection that we're going to be using, and that's because the type of grounding method will, as we'll see, will vary between the types of the amount of short circuit current that's going to be involved in our power system. It affects how we model our power system, all our models, how we, in our short circuit calculations and our coordination study programs, how we model all of that. And it affects the voltage characteristics during faults. We'll talk about that. And as I mentioned, ultimately determines the type of protection system that we use. There are three main types of grounding system on the distribution system, as we refer to the ungrounded or delta systems. These type of systems are designed to maximize uptime, because in this system, a face-to-ground fault, because there's no return path to the drawing on the right, there's no return path for ground current to flow. There's little to no ground current. There is some capacitive, straight capacitive coupling to ground, but that's impedance-wise, that capacitance is pretty high, so it limits ground fault current to very, very low levels, if none at all. So if I do have a ground fault, since I don't have ground fault current flowing, that means I can keep my equipment in service. Right? I'm not overheating them. I'm not going to cause damage to them. So this type of systems are designed to maximize uptime. You don't see them too much in a distribution system, the ungrounded delta systems. Where you see them most is on generator connected facilities. However, there are some municipalities in the United States that operate an ungrounded system. Again, I think they're in California. There's a couple of them that I can remember. And these require very specialized type of protection. We're not going to talk so much about in detail about the protection for ungrounded systems. But then the second method is the solemnly grounded system, which is a single point ground, usually at the utility distribution transformer. And for this, there is a path for ground current to flow. So if we have, for this example, if we have a face-to-ground fault in C phase, we have a path for ground fault to flow through the grounding into the earth and back up into that short circuit, and that current can be very high, as much as high as the phase fault currents. Now, one thing I should mention with the ungrounded or delta connected ground when you have a fault on the power system, a phase ground fault, what you've done is you basically bypass that neutral, that one winding of the transformers. So that winding is essentially now the neutral. So what you've done, you've shifted the neutral point of the system to C phase. When you've shifted the neutral point of that system to C phase, what happens to A and B phases? A and B phases are elevated to phase voltage. So A phase to ground, B phase to ground approaches the square root of 3 times the nominal phase to ground value. In that case, what happens, we need to design our system so that the insulation level of the system can handle phase-to-phase voltages. So it should handle phase-to-phase voltages with some, obviously, margin in there to be able to deal with, if you do have a ground fault, to still be able to keep the system in service and not damage the insulation. One of the problems with the solidly grounded method is the touch and step voltages issues that we can have. So if you do have some sort of ground fault in the system, and depending how good your ground is from your transformer to your ground mat, you could have some ground resistance. Maybe you've designed it properly and it's very small, but over time that might deteriorate and you might have some sort of ground resistance from the transformer going into the ground mat. And that can cause what we call touch and step voltages, which can be a little bit dangerous for personnel. And depending on the type of equipment that we touch, where the fault flows, where the fault current flows, where we are on the ground mat, we can experience some level of voltage that can be dangerous. Now, another type of grounding method is what we refer to as resonance grounded or Peterson coil grounded. This method is not so much, again, used in North America that I'm aware of. Again, very few utilities or municipalities that I've seen this on, but it's pretty popular in Europe. So a lot of this methodology they use in Europe. Basically, in this method, there's a reactance that's placed in the neutral of the transformer, and that reactance is tuned to the fundamental frequency with the straight capacitance of all feeders connected to that transformer. Now, if you tune that reactance properly, the neutral reactor and straight capacitance will cause small amounts of fault to flow in opposite direction to the fault point, as I'm showing in this picture. What happens is they cancel out each other. So essentially, at the ground fault location, there's no ground current. So the ground currents are very small, and even because they're cancel out each other at the point of ground, it's basically zero or very small. So one good thing about this is obviously arcs are self-extinguished. So if you do have a phase to ground fault, because there's no fault current flowing into the ground, the arcs can self-extinguish very quickly. The touch and step voltages, the dangerous or can be dangerous touch and step voltages we talked about, are very low, so it's not dangerous for personnel. And basically, intermittent ground faults are avoided. The disadvantage of it is obviously the same like the ungrounded system. The insulation level has to be designed properly for the high voltages that you're going to experience in the unfaulted phases. So, for example, surge arresters might need to be designed higher insulation levels and so on, disconnect switches and so on. It has no effect in the case of arcing cable faults. The cables can produce repetitive and harmful strikes, so when we're talking about underground. Tuning is an issue, right? Because tuning that reactance to the power system can be very difficult. So Depending on system conditions, that tuning might have to change. So it's that to keep that reactance tuned properly is a problem. And the biggest disadvantage is, to me anyway, as a power system protection engineer, is you need to apply special protection schemes for this, because there, again, remember I talked about ground fault current being high is not necessarily a bad thing. It's easy to set protection systems for that. For this case, there is no ground fault current, so protection systems they require special thoughts and special application. And then we have the resistance. So the ungrounded and resistant grounded systems, you probably know, as the two most popular methodologies here in North America to operate, that most utilities, most municipalities operate their distribution systems with. So this is what we refer to resistance or reactive grounded. So it doesn't, this reactance or resistance that's installed in the neutral of the transformer, it does not limit the short circuit to very low values like the high resistance or the Peterson coil or the ungrounded system. What it does is we select a resistor is to minimize the impact of the short circuit current. So we basically get it down to manageable levels, right? And because of that, because now the resistance is not between the neutral point of the transformer to ground, is within the transformer equipment itself, it reduces the touch and stop voltage problems that we talked about. Again, the disadvantage of it is, like the ungrounded and the Peterson coil grounded, is it does change the neutral point of the system. And for phase to ground faults, the other phases, the unfaulted phases, are elevated in voltage, so insulation design needs to be taken into account, some more robust insulation design. So let's talk about the distribution system protection components. We talked about some of them briefly, but just more of pictorially how it looks like in a whole picture. So we have our source being our generator or maybe our utility. Then that source gets fed into a distribution feeder, and that distribution feeder is get fed into a distribution sub. That distribution sub then is going to have a step-down transformer. It's going to step the voltage down to the manageable levels at the distribution level. So it might step it down, for example, transmission voltage of 345 kV to 13 kV. Most of that I know, most of what I've dealt with, it's usually 138, 69 kV down to 13, 4 kV, 33 kV, that kind of range. Just then we have the distribution bus, and distribution, as the word suggests, it distributes that power now to various components in our power system, various loads in our power system. So we have a distribution feeder breaker that comes from that distribution substation. Then we might have an overhead lines or underground lines that go out into the world, to where we want where our loads are. And there might be branch circuits off of that distribution line. Now, the distribution line, it could be overhead, it could be underground, or it could be a combination of overhead and underground. So leaving the substation, it might be underground for a short piece of distance, and then it comes back overhead into some sort of residential area. And then, depending on where we are on the feeder, we might have these branch circuits to branch off to go to our loads. And those branch circuits might have fuses on them. And then we might sectionalize the feeder. We're talking about sectionalizing it into various segments, and we can add a sectionalizing switch to be able to sectionalize in this feeder example. We have two sections with that sectionalizer switch. So if we have an issue with these portion of the feeder beyond the sectionalizer, we can open that up and keep all the loads on the left of the sectionalizing service. And further, to sectionalize the feeder, we use auto reclosers, and auto reclosers are there to help us to maintain some level of reliability to power systems so that a disturbance on the power system does not take all our loads out. So for example, if there's a fault, say at the end of the feeder to the right, if we didn't have reclosers on it, and the fault is not on any of the branch circuits where the fuses are, it's in the end of the feeder there. What we have to do is if we didn't have auto reclosing, we would have to trip the main circuit breaker. And by tripping the main circuit breaker, we've now caused outages in all of our loads. Whereas if we stuck that middle recloser in there, if there's a fault out on the right of that feeder, that recloser can open to isolate that fault and maintain the loads between that breaker and the other recloser. So we kind of talked about this a little bit when we talked about breakers, auto reclosers, and fuses, but the various components of how do we interrupt faults? How do we take that fault out from the power system? Fuses, we talked about. So all of these branches have fuses on them. So if there is a fault on one of those branch circuits, then that fuse will blow and take that branch circuit out of service. And it also protects us from having to trip the circuit breaker and take the entire feed out of service. So it's another method of being able to keep or minimize the impact of that short circuit to only have to open up the fuse that's associated with that branch. The various types of fuses, the most that's used in today is the expulsion type fuses. And these might be, fuse cutouts. So that's the most popular type. And that's because you can go up there if a fuse does blow, or you can go up there, a utility person can go up, take a hot stick and grab that fuse, pull it out of the fuse holder, replace it with a new fuse without having to climb that pole. So it makes it very easy to be able to do that, to replace fuses. Reclosers we talked about. It could be single phase or three phase reclosers. They could be, most of the time you'll see the reclosers on overhead portions of the distribution line on pole top, but not to say that there are cases where they might be in underground sections on pad mounts, or they could be at the transformer at the substation on pad mounts. And you have the circuit breaker. So you might ask if I can have the recloser, a pad mount recloser, if I can have it at the substation, why do I need the circuit breaker? Capabilities. The recloser, as you can see with some of the ratings, the continuous rating, the reclosers are only rated for certain continuous rating. And breakers are more robust pieces of equipment. They can be higher continuous rating. And most importantly is the short circuit interrupting capability. The circuit breaker has a much higher short circuit interrupting capability than a recloser. So that helps us because at the substation, if there's a close-in fault in the substation because of the transmission, the very strong transmission source behind it, those short circuits can be very high, and you need a piece of equipment that will interrupt high short circuit. Now, if your short circuit is low and your continuous rating is low, there's no reason you could not replace the circuit breaker with a recloser or pad mount reclosers. There's no reason you couldn't. I've seen cases where people are doing that because obviously it's cheaper, more economical, easier to install, easier to replace. So there's some advantages of doing that. But for the most cases, you'll see circuit breakers because of the capabilities that we need, specifically the continuous rating and the short circuit interrupting rating. So with each device that we're talking about, there's a rating or capability that it could that it could do. And when we talked about the recloser, we talked about the interrupting capability. The fuse is the same thing, except the fuse has also a curve associated with it. meaning the fuse, when it sees fault current through it, it does not open up or melt clear immediately. It starts to melt. So we can see this curve here. The blue line is when it first sees that high fault circuit current, it will start to melt, or we call the pre-arcing time, where it starts to melt, and then it will totally clear or extinguish the arc, or what we call the arc clearing time on the red curve. So there's a period in between there where it starts to melt, and then at the blue curve, and then at the red curve, then it completely clears that fault, completely blows the fuse. Whereas an auto recloser or a breaker, they need some sort of intelligence to tell them when to interrupt fault currents or short circuit currents. And that intelligence usually comes from our protective well, not usually, but it does come from our protective relays. So I think of it as the recloser and the breaker as the muscle, and the relay as the brains. So the relay has the brains, he's telling the muscle what to do. So with each breaker, with each auto recloser, you would see some sort of intelligence associated with it. We'll talk about a little bit more about that. But commonly, auto reclosers are commonly pad mounted, pole mounted, sorry, but there are cases where they can be pad mounted for underground applications. Usually deployed in distribution class voltage levels. In a transmission level, we don't use auto reclosers. We use the breakers as auto reclosers because of short circuit current. It's much higher because of all the sources in the transmission system that reclosers are not going to cut it to interrupt short circuit currents and for the continuous rating. So they're relegated mostly in the distribution world. Now, circuit breakers, all right. As I mentioned, they're capable of making, carrying, breaking currents and exceeded amounts of currents. Some of the higher circuit breaker that I've been involved with are 63 kA interrupting capability. It's a lot of current. And that was when I was working in New York City, so you could tell the fault in such a close connected grid, how much fault current you'll see on the system. And I'm showing in the bottom picture here, I'm showing the relays or the brains behind it. So the relay is the one that's responsible to telling the circuit breaker what to do. So the relay tells it to open. Hey, I've sensed the fault, you need to open. It sends what we call a trip signal to the circuit breaker, and that contact or trip contact will then energize the trip coil of the circuit breaker. There might be an auxiliary relay before it hits the circuit breaker. So for example, if I have a bus differential relay which needs to strip multiple circuit breaker to isolate that bus fault, the relay might go to the trip coil of an auxiliary relay, which then has multiple contacts on it to then trip all of the circuit breakers. However, with modern microprocessor relays, there is never a need to have to use a lockout relay because modern microprocessor relays have the I/O capability. They have enough outputs to be able to trip multiple circuit breaker, and those output contacts, if you get them in high break solid state output contacts, they are also capable of interrupting the trip coil current. So there's no reason that you have to have a lockout relay. And most of today's world have gone away from the lockout relay. Or auxiliary relay. They've gone towards stripping directly from the microprocessor, and we refer to that as a virtual lockout. So the microprocessor now then becomes the lockout functionality within the coding or the logic of the relay becomes the lockout function, and that's why we refer to it as a virtual lockout. So as I mentioned multiple times already, but I tend to do that before I get to the slide that I'm actually want to make the point, but just to reiterate, the protective relay is the one that needs to take the corrective action to sense that fault. and give the circuit breakers the signal to interrupt that current. So what our goal is to minimize and prevent damages to the faulted equipment, isolate that fault, right? Reduce the fault duration, right? Clear it as soon as possible, and allow the non-faulted parts or the normal parts of the power system to continue operating. So how do we do all of that? We do that with feeder protection on the distribution system. So we'll talk about some of the basic principles of feeder protection. So what is the goal of a feeder protection? Usually when we talk about protective relaying, we talk about the art and science of protective relaying. And what is the science? The science is the actual, calculations that determine short circuit and to set the relay to be able to trip for that short circuit. So for that relay to detect feeder short circuit currents, to detect faults in the power system, and initiate isolation of the faulted section. But that's not so simple. Anybody that ever set a relay has known that there's some art to it. So the art part is to accomplish that science with having minimal impact to the rest of the power system and customer, and that sometimes requires compromises. For example, you might want to, there's a very but there's a piece of equipment that's very old, and that if it's subjected to high short circuit currents for long periods of time, it's going to fail permanently. So you might want to set an instantaneous overcurrent element on that so that you trip as soon as possible. An instantaneous overcurrent element we'll talk about, it's an overcurrent element without any intentional time delay on it. However, the consequence of that is if you have a fault outside of that piece of equipment zone of protection, or it's, for example, it's a transformer that goes into that's feeding some sort of load. If you have a fault on the load side, that overcurrent element can be susceptible to pick up and trip, and you're unnecessarily taking out that load or parts of the power system that you normally wouldn't need to take out for that fault just in that transformer. So you need to look at things that are, what is important to your process, what is most important to your process, and make those decisions. And sometimes it does come with compromises to be able to, to reliably set those relays so that the impacts are minimal to the power system and to your customers. So let's talk about the protection problem. What happens? So we have a typical industrial facility here with a single source and a number of feeders or off of that source, a number of breakers off of that source. So what happens if we have a fault, for example, on line B, which is associated with breaker number 3, distribution breaker number 3? What pieces of equipment will see that fault? Well, fuse F1 will see that fault, right? Fuse F1 will start to melt, it sees that fault. Breaker 52.3 will see that fault current also, right? And its protective device will start to initiate tripping. Then breaker 52M will also see that fault, and it could start to initiate tripping. And the utility feeder might see that fault depending on the impedance of that transformer and how it's set. It could see that fault, and it could also initiate tripping. So we have to prevent the feeder relay, the main relay, and the utility relay from tripping for a fault out on line B. We want only the fuse to operate. Right? And we do this by coordination, by coordinating the various devices to trip in sequence. So some terms when we talk about coordination, I'll talk about a lot about downstream and upstream. So upstream is the source side. So if, example, recloser on the main feeder, not the recloser on the far right, but the recloser on the main feeder. If say I'm sitting at that recloser, upstream to me is going to be everything from that substation, distribution, including the transformer and the generator, everything to the source side. And then the downstream side is going to be everything on the load side. So all of those fuses and the other recloser will be on the downstream side of that recloser. So if we do have a fault, for example, let's see on this recloser to the right, if we have a fault in that section, we want the main recloser to coordinate with that right recloser so that it allows the recloser on the right to trip first before it trips. And then the main feeder relay, the distribution station, needs to coordinate now with that main recloser. And then the utility relay on the other side of the transformer will then need to coordinate with that distribution relay. So you can see there's a lot of coordination. And what we refer to that is stacked coordination. So multiple devices that are coordinating with each other, they stack up on each other. And there's a problem with stacking coordination. Stacking coordination, too much stacking of coordination will slow down tripping time significantly. So for a fault out here, if that fault, because we need to coordinate for faults on the recloser all the way to the end of the circuit, if there's a fault on the main feeder, then we're going to be tripping slowly because that feeder relay needs to be coordinated with that end recloser, even though its fault is not at the recloser location, it's at closer to the substation, but we still, because we're coordinating with that end recloser, it's going to slow down the tripping of that substation breaker. So what we typically use, the ANSI numbers for overcurrent protection is the 50-51, the 50 being an instantaneous overcurrent element and the 51 being a time overcurrent. And overcurrent is one of the most simplistic protection types of protection systems to apply. It operates in a predetermined current level, we refer to as the pickup level. So we need to set what predetermined level of current we need to for that relay to trip on. That's usually referred to as the pickup current. So all relays, overcurrent relay, will have a setting of pickup on it. There are other types of overcurrent relay, which one is the directional overcurrents and the differential overcurrent. We won't talk so much about them, but the directional overcurrent, the only difference between it and a normal overcurrent element is it will only see faults in one direction. So you just need to set it to which direction you need to see the fault. But typically, as we talked about in our distribution system, faults are only going in one direction anyway, because the source is behind, it's upstream. So you don't need to usually worry about to directionalize overcurrent protection unless there's a source like a generator or something that you need to take care of. So the common protection elements, as I mentioned, the 50-51, then the 67, which is the directional element. The directional element also needs a polarizing signal. The polarizing signal tells it, what the direction is of that fault or that load that's going through that CT. So that usually comes from either a VT, a neutral CT or neutral CT of the transformer, or negative sequence positive, for phase faults, positive sequence voltage, for ground faults, zero sequence voltage or negative sequence voltage are the polarization sources. So in addition, for a 67 element, in addition to the CTs, we need VT connections or another polarizing source, as another CT that's upstream of that relay. So the typical overcurrent protection, we talked about the power flowing usually only in one direction, and we refer to this as a radial feeder, meaning if current is always going to flow in one direction onto that feeder, it's a radial feeder. If currents can flow in both directions, we refer to as a loop feeder. And a loop feeder just means that there's a source at each end of the feeder. So the short circuit current that we calculate will determine how we set the relay. Overcurrent relays are simplest. This is most of the simpler type of protection. Inexpensive if you apply it in the most simple manner, but we'll talk about some, some things that we can do with microprocessor relays that's beyond the overcurrent protection that gives us a lot of value. If they need to coordinate with downstream devices, we need to add time delays on them. When we talk about time delay, we'll talk about two types of time delay: definite time delay and inverse time delay. We'll talk about what that means. They can be slow if they need to coordinate with things downstream. They are selective. If they're coordinating properly, they are selective. Selective meaning they're only going to trip for faults within their zone. They're not going to trip for faults, for example, on a feeder branch that has a fuse on it. But we're sacrificing speed because we need to slow that down to coordinate with that fuse. We can use to speed up that process to be able to trip faster and not have to coordinate. We can use communication seams to be more selective and make that to speed up that tripping. An overcurrent, instantaneous overcurrent element, as I mentioned, there's an overcurrent element with no intentional time delay. It's probably about a cycle usually because of just the algorithm of the relay. The A to D converter, the relay has to convert that analog signal to digital signal and has to sample it, it has to filter it. So it's not instantaneous in a sense. It just takes about a cycle. And what that looks like on a curve is when I set the pickup, anything in that shaded region, it will trip first. So anything above the pickup and above one cycle. So any fault that is above the pickup that I'm set, say the pickup is 1 per unit. And if there's a fault anywhere above 1 per unit and that lasts more than a cycle, that overcurrent, instantaneous overcurrent element will pick up and trip. So coordinating, so if we use an instantaneous overcurrent element, how do we coordinate? So the red relay on breaker B, that can be set basically instantaneously where it's just a 1 cycle delay. So it'll pick up pretty fast for faults within its zone beyond breaker B. But breaker A, the blue relay, since it needs to coordinate with the red relay, it needs to be more than a cycle. It needs to give the relay enough time to sense that fault. So we need to have some sort of delay between the red and the blue relay. And that time what we refer to is a CTI, or the coordination time interval, or coordination. There's various terms for them. I usually use the CTI, coordinating time interval. I'm trying to remember what the other terms are right now, and I'm drawing a blank. Sorry. Then we have the inverse time overcurrent relay element. It provides some delay before the element operates. So for anything close to the pickup, you can see the time is much higher. What that helps us to do is it helps us that there's small fault current levels. Could be transient in nature or self-clearing in nature. It helps us for that, to be able to say, hey, the fault is not permanent in nature, give it some time to clear itself. However, for high fault currents that can be do more damage to the power system in very shorter amounts of times, it's going to trip faster. So the higher the current is going to trip faster. So the tripping time varies inversely with the current. The higher the current, the lower the trip time. There are various different types of curves. Inverse, very inverse, extremely inverse, definite time, moderately inverse. And it will depend on the application, which curve you want to use. Again, the extremely inverse one will be if you have for low levels of fault currents, you want to be able to wait for a longer period of time before you trip, but at the same time, you don't want to compromise tripping for higher levels of fault current. So extremely inverse, whereas the definite time or moderately inverse basically is going to say, hey, for high fault currents and low fault currents, I want to trip about the same time. I'm not going to wait too much between the two. So it all depends on the application. And coordinating is similar. So once you've selected the curve for the relay and breaker B, the red relay, to trip for all types of fault, you want to coordinate on relay A or feeder A with the same type of curve. So if you've chosen a very inverse curve, which is the most common curve that I've seen used as a very inverse and inverse curve, then you want to also select a curve that's pretty close to that. So you want to definitely select an inverse or very inverse curve. You don't want to select a moderate or extremely inverse curve because you might have miscoordination between the two relays. Once you've done that, select similar curves, then you just have to stack them and say, hey, the blue curve has to be, coordination time interval to the red curve from the blue curve has to be, say, for example, 0.3 to 0.4 seconds. And now you allow breaker B to trip for that fault before breaker A trips. We talked about the 67 element, and usually the 67 or the directional overcurrent element is only usually set when you have some sort of generator in your facility or some sort of large motor, that can have power flowing in reverse directions. Ground fault detection, balance load is near zero ground current, but when a fault occurs, there's high level of fault current, and depending on this power system grounding, which is usually if it's a resistive grounded system, it's going to be some level of your load, magnitude of your load, and it's going to be some level of magnitude to your phase fault current. Now, the beauty about the ground current overcurrent protection is I can set it more sensitive than my phase overcurrent, because my phase overcurrent, I have to set it to trip for faults, but at the same time, I don't want to set it to trip for load currents. So I have to set it somewhere in between my minimum fault current level and my maximum loading on the feeder. Whereas in a ground overcurrent element, I don't really need to look at loading in the feeder because during normal conditions, my feeder is balanced, so I should see very, very little close to zero ground current. Of course, if you have a very unbalanced power system, then you have to take that into consideration. But most of the power systems, especially, are pretty balanced during load conditions. Then the type of protection that you use with the CTs that are connected for ground current protection, there's two types of connection. There's the residual current connection, which basically can use either a CT that goes across all three phases, or we can use the residual connection of the three-phase CTs. Fortunately, I'm not showing the residual off of the three-phase CTs in this slide problem. Or I could have what we call a zero sequence connection, where the CT is a very sensitive CT, ground CT, that's going across all three phases. And it's the difference between the two methods is the residual connection is only as accurate as your phase CTs, because your phase CTs are giving you a ground current. Whereas in the zero sequence connection, I could be very much more sensitive because my ground CT is more sensitive, so I can have more sensitive settings for ground faults. The problem is the installation of the ground zero sequence CT. Now I got to fit three phases, all three conductors, all three wires into that hole on that CT, and I got to ground that CT properly. So the installation might be a little more difficult. Automatic reclosing. So when we talk about distribution systems, especially overhead lines, a lot of the faults are temporary in nature. Lightning strikes, conductors blowing trees onto the conductors and so on. So we want to be able to clear that fault. We don't, obviously we don't want to leave the fault on there because we don't know if it's permanent or temporary. So we want to clear that fault from the power system. We want to wait some time, and then we want to re-energize the power system automatically so that if the fault was temporary by nature, then once we've restored the line, the fault is gone, and we're can restore the loads in very short periods of time. So what happens is for the reclosing is the recloser works in that it senses the fault, trips the fault, waits for a certain period of time, then closes back that breaker or recloser into the fault, not into the fault, but into the power system. And if that fault is still there, then it should retrip. And if the fault is cleared, then it goes about this normal operation and the load is restored. This is, so as I mentioned with the breakers, the auto recloser is a dumb device also. So it needs some intelligence to tell it all of that. It needs some intelligence to tell it when to trip and when to close back in, right? And that's done by a relay. And that relay is usually part of the auto reclose package. It's in a cabinet that we install to the pole, various locations in the pole, and it has connections to the auto recloser. And it's usually it's a plug and play solution. Basically, a recloser might give you like a 25-pin plug connector, and we plug into that recloser connection, and we're done. We just set our relay and we're done. Coordinating for distribution circuit protection devices. We talked a little bit about coordination, what coordination gives you. It gives you selectivity. We talked about some of the problems with coordination. If you stack too much, you're going to have high clearing time. This section is really talking about how do we coordinate, what goes into determining coordination settings. So as I mentioned, current flows in many devices. So sizing and coordination of those devices are very critical. So sizing your fuses, sizing your breaker. So the fuse at the bottom of the panel board, because it feeds some sort of load there. It's a 200 amp fuse. Then because there's no load off of that break, the main feeder there, that breaker could be fused, could be rated at 200 amps. But once we go up to the source or the utility or the main breaker, that has to be a higher rating because now it's getting current that feeds all three of those feeders. So you have to be careful when you're rating equipment. You need to know what the application is, where that equipment is going to reside in your power system. Let's talk about the fuse. How do we coordinate with the fuse? So we mentioned the fuse has a pre-arcing time and a total clearing times. And the pre-arcing time is when you strike the fault, the fuse starts to arc, and then finally when it completely clears or melts to clear the fault. So what do we coordinate? If we're coordinating fuse to fuse, we want to coordinate with the clearing time of the downstream fuse and the pre-arcing time of the upstream fuse. So the pre-arcing time of that blue curve, the fuse in the blue, the clearing time should be larger than the total clearing time of the fuse in green. So we want to coordinate with the pre-arcing time of the blue fuse and the total clearing time of the green fuse. Same thing when it comes to relays. If we're coordinating a relay with a fuse, the relay curve will coordinate. The relay obviously doesn't have a pre-arcing and a total clearing time. It's just one curve. It's when it trips. So with the relay, we want to coordinate usually with the total clearing time of the fuses. Now there might be situations where you might need to coordinate with the pre-arcing time. There's a special situations where because you're at a point where it's very a critical feeder or some sort of important piece of equipment that cannot handle a lot of short circuits, so you might coordinate with the pre-arcing time, but generally you coordinate with the total clearing time. And again, the normal clearing time, 0.3 to 0.4 seconds, the CTI between those devices.
Front door closed.
So the recloser that I'm shaded there needs to coordinate with the fuse F3 and F4, as well as the recloser at the end of the line. So if you have multiple devices that you need to coordinate with, you have to choose the device to coordinate that has the slowest tripping time or clearing time. In this case, it's the F3 fuse, which has the longest clearing time. Because why? Because that F3 fuse might have to coordinate with the downstream fuse. So you can see the F3 fuse is on a branch circuit, but then there's another branch circuit in that F3 branch circuit that has a fuse on it. So that F3 fuse might have to coordinate with that downstream fuse, making it slower than the F4 on the reclosure at the end of the line. So in that case, we'll have to coordinate with the F3 because it has the slowest clearing time. Then the relay back at the substation, then he might just have to coordinate with the recloser or the fuses, depending again which one has the slowest clearing time.
Front door closed.
It's probably the recloser R2. Because why? Because that recloser R2 has to coordinate with F3, which in turn has to coordinate with another fuse. So that makes R3 pretty slow to begin with because of all the devices it has to coordinate with. So the rules for coordinating fuse, coordinating devices, I talked about coordinating with the total clearing time. You don't want the curves to touch each other because then you're going to have miscoordination. So this is an example of miscoordination. So my main feeder, I chose a curve, even though for low levels of fault current, like at F1, for faults at F1, I'm coordinated properly, but when I get a fault at F3 or F2, I'm miscoordinated where my main feeder is going to trip first before the distribution feeder. And that's not good because then I've cleared the main feeder and I've not only taken out not only have I taken out that feeder that's associated with the fault, but I've taken out all the other feeders within my substation or my industrial site. So all we have to do is we either have to move this curve up to be able to coordinate with that feeder. And then again, for a loop feeder, just a quick example for a loop feeder, all we've talked about was a radial feeder, but remember I mentioned there's also loop feeders. So in this case, breaker 3 at the bottom is what we call our tie breaker, which ties those two feeders together, creates a loop between substation X and substation Y. So now currents can be flow in either direction. So in this case, how do we set our coordination curve? Right, so what is our slowest curve is going to be when I'm looking from, for example, bus X to bus Y is for currents for faults on bus Y. In that case, I need to coordinate breaker 1 with breaker 5 and so on and so forth. So then breaker 1 will then have to coordinate 4. 3 would have to coordinate with 2, and 2 with 1, and so on and so forth. So there is a method to speed up this tripping time because again, you could see the stacking of coordination. If each one of these coordination time is 0.2 to 0.3 seconds, I'm talking about 1, 2, 3, 4 stacks here. So 4 times 0.4, that's over a second of fault clearing. If the fault is between breaker 1 and 2. It's a long time. So to be able to, there's some methodologies we can use to speed up that coordination time. And this is using zone interlocking. So basically what we do is we sense when, for example, feeder number 2 senses a fault on its zone, it sends a blocking signal to the source CB1 and CB2 feeders saying, hey, don't trip. I see a fault in my section. I'm going to trip first. You guys hold off from tripping. So what that allows us to do is set fast overcurrent elements in CB1, CB2, and CB3 so that we don't have to wait for CB3 to trip before we trip. We can set a fast overcurrent, but then at the same time, it's going to be blocked when we receive the signal from CB3 saying the fault is in this direction. However, there's a little bit of coordination time that you have to put in because it will take some time for this relay to operate and send that signal. So minimum amount of time, we're talking about maybe 30 to 40 milliseconds at minimum. So it's a far cry from the 0.3 to 0.4 second coordination time or the 1 second coordination time that we talked about when you stack them, right? So we're drastically reducing the clearing time. Why is that important? Because what if we have a fault on the bus, then we're allowing that bus fault current to be on that bus for over a second. That can have disastrous consequences because that will heat up the bus, maybe even cause the melting on the bus, cause the bolts to, the metal to buckle. So it can cause permanent damage on the bus. So we want to be able to clear that bus fault as soon as possible. Also arc flash issues, right? We want to be able to clear as fast as possible. So this is one methodology to be able to do that. The problem with this methodology is it requires that all of these feeders be in a general location, right? So if you have an artery closer out in the field somewhere, it might be more difficult to do that. You might have to use like a wireless system, and that's okay. It just requires some more equipment to install, like our MDS radios or Orbit radios or our cell radios. We could use that to be able to do zone interlocking if the relay or piece of equipment is out in the field somewhere where you can run a direct wire into the substation. Let's talk a bit about redundancy before we get in some hands-on the 850. In a typical no redundant application, which is probably in a lot of industrial facilities that I've seen, is basically this is the architecture usually. So is no redundancy, being that if there's an issue with that feeder, the relay and feeder 52.3, for example, then there's no protection on that feeder. You're relying on the coordination of the main feeder to trip for faults in that feeder number 3. So you might have to deal with some slow tripping if you have issues with your feeder overcurrent protection or feeder overcurrent circuit. That's okay if you're able to live with that, which you could speed up by having a draw type relay. So that helps you to be able, if there's a problem with the relay, replace the relay very quickly, not have to deal with any wiring, put it back in service, and you're good to go. Just remember to save the settings of the original relay. Always save your settings with modern microprocessor relay. It's easy as just connecting to the relay with a laptop and pushing a couple of buttons, which we'll go through in a little bit. Now, if you want full redundancy, you don't want a single relay going down to take out your process or take out protection for your process. And of course, it's process driven. So if the process is very important, it's making you a lot of money. So you want to be able to have reliability in that process. So you might have 2 relays. Redundancy, full redundancy is a requirement for most utilities I've dealt with. Not so much for industrial. Again, it's for industrial, it's more process driven. So the economics of scale comes into the equation. However, we can have a compromise where we can have redundancy with a dual feeder relay. So basically what this relay is doing, it's instead of having one relay protect feeder 1 and 2, one relay feeder 1 and one relay feeder 2, what we'll have is this relay can protect 2 feeders. And so that if we have 2 relays that can protect 2 feeders of the same feeders, then we have redundant protection. So if one of this relay goes down, we still have protection in the other relay for both feeders. It's with the previous full redundant one, obviously it doubles the number of relays that you need. With the dual feeder methodology, it does not double the number of feeders. It's the same number of relays that you need. It's just more wiring. You have to wire those CTs into that switchgear, but usually, hopefully, they're right next to each other, so it's not a big deal to wire that. And then we take it, we talk about the full picture of the distribution system beyond, the recloser, the feeder relay. There is, high tension facilities or low, medium voltage industrial facility, which is it's not a full industrial facility, like maybe like a shopping center or something. And then we have pad mount switchgear there. And with those pad mount switchgears, for reliability, they have a number of different source or ways that come in, and then they have a number of different outputs that go out of those ways. So with a typical pad mount switchgear, you might have up to 4 or 5 ways. Typically, you would need about 4 relays to protect that pad mount because you need 1 for each way. With the 850P, it can protect the entire 4-way pad mounts in one device, so you don't need 2 devices. And it's all about consolidating it into one device. And thinking more outside the box now, have this relay, it's a microprocessor relay. There's so much other functions. We'll probably do a seminar on arc flash later on. We'll talk about how to use it to do arc flash protection. How to do zone interlocking protection over fiber optic with Goose messaging, so on and so forth. But I want to just highlight something that was kind of way outside the box for me. So the 8 series relay can act as a Modbus master, and this particular company had these switchgear sensors that were installed in the switchgear to sense conditions in the switchgear, humidity, temperature, and so on. So the environmental condition in the switchgear. So instead of having separate comms for this device, since the relay is already in that switchgear, we can connect those devices to the relay and gather the information from that device into the relay. Not only now that you have the information, which you can then send back to your SCADA system via the relay, which you're going to have to connect to your SCADA anyway, without having to have another redundant comms pad to the sensor. It also puts the electrical and environmental data together, so you can correspond and correlate them very easily by looking at one device instead of looking at 2 devices that have to put the times together and so on. So again, it helps with your monitoring, with your diagnostics of your switchgear. You might see things going bad. You see all of a sudden you might see like arcing currents, and then your temperature goes up in your sensor. You want to correlate those things. So that's the end of the theoretical part of the presentation. Just wanted to go through some of the 850 setup software. So we'll take the next 15-20 minutes to do that before we take some questions. Hopefully Paul has answered some of the questions that you guys have out there. So in the 8 series setup software, and this is true for any 8 series relay, including the transformer diff, the generator relay, the 889 or the 869, which is the motor relay. The setup is similar, where you have an online window on the top and an offline window on the bottom. In the online window is, as the name suggests, is when I'm connected directly to the relay. So I have a relay on the bench. This is an 850D relay. I'm connected to this. So there's 2 ways of connecting to the relay. One is a quick connect method, And this is what I've done. I've connected to here. So I'm going to connect as observer means if you just want to connect to the relay and look at the parameters in the relay, just read settings, read oscillography, look at the settings, then you can log in as observer. However, if you want to make changes to the relay, you need to log in as admin to be able to make changes in the relay. The default password is 0 for all 8 series relays. So now we're connected live with the relay. Before I go into the relay, I want to just mention the 2 connection methods. So the quick connect would be a way if you just very simply go up to the relay and you want to quickly connect to the relay and you just want to walk away from it. So it's a very quick method to do that. However, there's another method to the device setup. With the device setup, if you have multiple relays in your system and you want to be able to just walk up to one relay and connect to that relay without doing anything, what you could do is when you're doing your commissioning, you could set up multiple relays in here to be able to connect to them. It will save the serial number, all the settings, everything for you, and then you can then grab that to your offline window to save them locally on your computer, so you have a record of everything. And then later on, when you go back to your relay, you could just connect to that relay and it will tell you whether you connected to the right relay or not. So right now I'm connected through Quick Connect. And this is the basic menu of the relay. One of the things I just wanted to show you is, I don't have my camera on my relay, but in the software it gives you a mimic of the front panel of the relay. So whatever is happening in the relay, my bench right now, you'll see it right here. So you can see a couple of alarms up right now. There is an alarm that's blinking, telling me there's something alarm message there. The in-service LED, very important LED. Whenever you walk up to an 8 series relay, it has to be green. That in-service LED has to be green. Anything other than green, there's a problem with that relay. If it's like it is now, if it's yellow, there's a problem with the relay. If it's off, there's a problem with the relay. If it's red, there's a problem with the relay. Anything other than green, you need to take a look at. Something's going on. And the alarm, it basically tells me there's something up on the alarm. So what I'm going to do, I'm going to click on the home button, and that's going to take me to the home screen. And then I'm going to look at the targets. I'm going to click the button under the targets. That tells me those alarms that are up. Right now it says the breaker is not configured because I'm connected to the, this is a default setting file I have in here, so I haven't set up the relay. The relay is out of service. So by default, when the relay comes from the factory, it's out of service, meaning the protection elements are not, even if you set the relay is still disabled. You have to go in and manually tell the relay, hey, now I'm putting you into service. So we want you to make the concerted effort to say, hey, now I'm putting you into service. I'm taking responsibility for all the settings, everything that's in there that's been set up properly and it's been looked into properly. And that once I do that, that will go green. So let's go into the installation and put this relay in service. Right now I'm connecting live to this relay, so if I put it in service, change it from not ready to ready. Okay. So see that LED goes green. If I go back to my target screen, that alarm will go away. So that relay not ready goes away. My relay has, the 8 series has Wi-Fi settings in it too, so that's why my Wi-Fi settings right now, since it's a new relay, it's a default setting, so that's why it gives me that other alarm. Now, a couple of things that I wanted to mention that are very important when you're connecting to an 8 series relay is the icons on the top here. So one is the the event recorder. The one on the left is event recorder. If I click on that, it will bring up the event recorder screen on the relay. And this is a live screen, meaning if there's anything changing in the relay, it will change up here. And you can see the last thing I did was make a setting change. So the relay recorded that in the events report. That was a setting change I made when I took it from ready to not ready. All the previous things when I logged in, when I logged out, what role I logged in with. I logged in with admin. When I change that setting, I place the relay in service, right? The next one over is the oscillography. Since this is a brand new relay, I don't have any oscillography in it, but this is how you download the oscillography. Very, very important, because I see a lot of people miss this, is to set up the oscillography properly in your relay. And if you go into set points under transient recorder, this is where you set up your oscillography. Because why is it important to have a good oscillography set up is because if there is an event, whether a relay tripped properly or didn't trip properly or misoperated or didn't operate properly, you can go into, once your event is triggered, the event report gives you a snapshot of the power system when that disturbance occurred. So you go and you get the analog the waveforms, all the data the relay is reading, all the trip signals the relay is experiencing in that oscillography where you can line it up. So it's important to set this up. By default, it's set to any trip. So whenever you set something up to trip, the oscillography will trigger. There might be other things that you want to trip on. Maybe you want to trip on pickup. Maybe you want to trip on motor starting. You know, there's a number of other conditions you might want to trip off of. So you could set that up in here. All your digital elements, you want to put all the digital elements that you've set up to trip here, so it shows up in the oscillography. And you want to set up these analog values. There's 16 of them. These are basically values that are calculated internally in the relay. So these could be power, apparent power, reactive power, real power. It can be any of the environmental data that's measuring. It could be anything that's calculated in the relay. So by default, the relay will give you, even if you don't set up these analog signals, it will give you all the currents and voltages that are connected to the relay. But these analogs are extra things that the relay is calculating internally, and you might want to see some of them, like maybe motor loading, you might want to see, or total harmonic distortion, second harmonic current, so things like that you might want to look at. That's important to you. So it's important to set up the oscillography. Next to the oscillography button is the protection summary button. I use this a lot. I actually use it for not only looking at customer settings, but actually setting up my relay. Usually I do it in the offline window, not the online window, so it takes a longer time in the online window because I'm connected to the relay in real time right now. So bear with us here. There it is. So it gives you all of the elements that are available in the relay in one screen. So you don't have to try to find those in the relay menu, even though it's fairly easy to find those. Set points are located under all the settings are located under the set points menu, and of course those settings has groups on them. So the device is all of the non-protection settings, like setting the time, setting the username, setting password, setting the transient recorder, the oscillography, the communication settings, how the front panel works, how some of the buttons in the front panel works, all of those device settings. And then the system is where you would set up how you're connected to the power system. You know, phase rotation, your CT, your PT values, and how your breaker. And that's where we had that error that the breaker is not configured because we had no auxiliary contacts set up to indicate the breaker status in the relay. The inputs are obviously all the inputs in the relay. There are a couple of types of inputs. There's contact inputs, optical inputs, which are wired into the relay. Virtual inputs, which can come from your SCADA system. Same thing with the analog inputs. Remote inputs are basically Goose messaging for IEC 61850. Then the outputs, your output relay, virtual outputs to SCADA, analog outputs to SCADA. And then your protection settings. There's 6 groups in the relay. So usually you would only be using one group. An application I can think of as having to have 2 groups is if you're doing arc flash mitigation with a maintenance switch. So you turn the switch on, the relay switches from setting group 1 to setting group 2. So in setting group 2 now it becomes faster. It will trip faster to mitigate arc fault events. Sorry. And so as you can see, the menu is pretty straightforward, but the quick summary gives you a quick summary of all the protection elements that are available and the ones that are enabled. So if I click on enable, it'll just show me the ones that are enabled. So that's a quick way of looking at it and setting the relay too. And I'll go in the offline window where it's more easier to see that. But the other icons is the metering screens. If I click on that, it'll bring up a lot of the metering screens in the relay. Currents, voltages, all of that, power if it's set up. Right now everything's 0 because I have nothing being injected into the relay. The I/O that gives you all the input-output statuses, all the contact input, the virtual inputs, virtual outputs, all of that stuff we talked about. I could see here that it's telling me the critical failure relay is on. That's okay because that's the normal condition. It's closed in normal operation, open in alarm. Now, the important one I just wanted to mention is this one. I'm not going to click it right now because it could take a while to download it. It could take up to a couple of minutes, so I don't want to take much time away from our session today. Is the service report, the one on the right here. And it's very important if you want us to help you to look at something, it's a problem with the relay, or you can't figure out, something that you've set in the relay, you can't figure out the relay might be tripping when you don't think it should have tripped. Anything that you want us to look at is, the first thing you should do is to click on this service report. What it does, stop me, I gotta close the device view. I'm not gonna actually download it, but I'll just click on it. What it'll give me where do I want to save it, where I want to save the service report. So I'm going to browse and I'm going to save it wherever I'm going to find it. And I click on OK. What it does, it grabs every single piece of data in the relay and zips it into one file. And then you can send that one file to us. So it grabs the settings, it grabs the events reports, it grabs the oscillography, it grabs the data logger, grabs diagnostic information, monitoring information, everything that's in the relay, it grabs, puts it in one file, and you can easily send that file to us. So if anything that you get out of this hands-on is how to connect to the relay and download the service report, I'll be happy. Now let's just go into the offline window. So the offline window is when you're working with the file and you don't have the relay in front of you, not connected to the relay, or if you're in the office. So if I go into protection summary, I'm gonna see something there. So for example, if I've done a setting coordination study, and I know that I need to set it, say for example, I need to set time overcurrent element, a neutral time overcurrent element, a ground instantaneous time overcurrent, and a phase instantaneous. So 4 elements. So I've done my studies, I've done my coordination studies, and I want to know, I already know what the settings are. I'm going to come here. First, I want to select the phase TOC is the first one. There's 4 TOC elements available, so I'm going to enable the TOC1 to trip. Now, there was a question on the that I'll address right now because we're on the screen. The question was, by default, relay 1, which is the trip relay, it shows as disabled in the settings. So let me go to that relay. So I could see here, nothing is set up to operate it. Operate is off. Nothing is set up to operate it. That's okay. Once you've selected trip on the phase TOC element here, it automatically will hit that relay. You do not have to come in and program it in the operate. The relay internal logic, once it sees that TOC2 is set up for trip, it will automatically hit that trip contact. So you don't need to go in and set it up in this screen. Now this operate here is if you had some like special type of logic or something that you've created in the relay, And then you wanted to include that logic to also trip the relay in addition to the TOC or any elements that you've set up with the function to trip. So, and then I say I want to set up it for 2 times CT. So when you set up the 8 series relay, it's always a unit of CT. So if it's a 1 amp or 5 amp CT, so for a 5 amp CT, this pickup is going to be 10 amps. For a 1 amp CT, it's going to be 2 amps. And of course, if for example, if it's a 2005, then it's a 4000 pickup, or if it's a 1005, it's 2000 pickup, and so on. Then the curve is what type of curve you need to select so that you're coordinating properly, right? So I'm going to select very inverse. And the time dial, how do we move that curve up and down? I don't just remind you of that. There we go. So remember, this curve is the one that's here. Let me just make it a little bit bigger here so you can see it. So this is one particular curve. So say, example, this is a very inverse curve or inverse curve. The time dial is just shifting the curve up or down. So it's increasing or decreasing the trip time of that curve that you've selected. So higher time dial will give it a longer trip time. Lower time dial will give it a lower trip time. So if this element is coordinating with something downstream, then I might see a time dial between 2 to 4, right? Because I need to coordinate with something downstream. If I'm not coordinating with anything, I might see a time dial of less than 1 because I want to trip as soon as possible. Important that you set up the targets to latch if that element is being used for tripping, if you want to see the target on the screen after the event. So you want to go in front of the relay, you want to look at the targets, you want to tell what operated for that event. You need to set that event to latch in. Otherwise, if the breaker trips and the event clears, the fault current goes away, it will automatically reset if this is not set to latch. So I'm going to save that. And you can see now that it's turned green and tells me that function is set to trip. I could also filter everything by enabled, so it tells me that function is there, set to trip. Let's just do one more. Say I want to set a ground TOC. Again, I want to set to trip. It's coordinated with something downstream. It's an inverse time curve, a very inverse. I want to set the targets for latched. On the pickup, I'm going to set lower because remember, ground faults, I can set it more sensitive because I don't have to worry about loading, tripping, unloading. Again, so I have those two set up, and these, once they've set the trip, they will automatically hit the trip contact and the relay for that. So another question that came up is when replacing a 750 relay with an 850 relay, what is the recommended way of transferring the protection settings? So let's briefly do that by going through an example of creating a new setting. So you have a relay, you want to create a new setting. So first thing you do is you right click in your offline window and you say new settings. Then of course you have to know the model number of the relay that you're going to put, but in the bottom here, it's pretty cool. We actually tell you what the model numbers mean. So if you click through this, so I'm going to say it's an 850D, it's a 5 amp CT, and I have 2 sets of CTs, a ground 5 amp ground CT. I have a high voltage power supply. I have some RTDs in there. I have a normal IO. I want to have a second IO card in there because I'm maybe trip multiple breaker because this is a 850D, so I might be tripping 2 breakers with it. Go through all of this. So I can create my model. Once I create my model, then I can click on OK, and it will create a relay, a blank relay file, a default relay setting file that I can then manipulate. However, if I'm converting a 750 to an 850, what I do is I click on this bottom where it says initialize setting from SR settings file. I put a check mark there. and I click and I browse to where that where that 750 settings is located. And then once I've located that 750 settings, I click on OK. Again, I'm not going to go through it because it takes a couple of a minute or two to do it, so I don't want to take away time from the presentation. What it will do, it will automatically convert those 750 settings to the 850 setting, so you don't have to worry about transferring the protection settings. It will automatically do it for you, and it's pretty simple how you do that. You just download the 750 setting file. However, you will need the 750 software to download the 750 setting file. What that looks like, it's very similar. It's called 750-760, and it's very similar to the 850. It has an online offline window. You quick connect to the 750, you download the setting file, and you save the setting file on your computer, so that you can then convert it to the 850. And to save the setting file, similar with the 750, 850, to save the setting file on your computer, you just right click on it and you click on read set device data. You have to be connected to the relay. You have to be logged into the relay. You tell it where you want to save it. I'm just going to say test for now, and then we'll start reading it. So you notice that to read the setting file, I don't need admin right. I logged in as the observer, and I'm able to read the setting file. So make changes when I want to write, say for example, I make changes to that setting file, I want to write that setting file back to the relay, then I need to log in as admin. Okay, so that's there. It's downloading that setting file there pretty quickly. And the folder that downloads it too, if you highlight it, it'll tell you what the folder it is in, so you can then copy that and email it to somebody if need be. And the same thing with the 750, and then you can then convert that 750 to the 850 setting file. So another question, Paul, are there any questions that I should address that came in the live chat?
Yeah. There's one here there's a couple. If you got a minute. This was back when you were talking about the impedance grounded systems and the Peterson coil. Somebody asked a question about Con Ed, and they, in reference to that slide, it was, is this why Con Ed likes to do ping testing? And I figure they're not talking about pinging the network. So I was hoping with your experience, you might have a better take on exactly what this person might be asking.
So Con Ed does not use Peterson grounds that are high impedance. They use a resistive grounded. So it is, what was it, 3B or 3A that I talked about. So, and I'm not familiar what that ping test is. No, I'm not sure. So if maybe that person can contact us offline to, if they want some more information to explain what the ping test is, and then we can figure out from there what they're trying to do. But typically, to my knowledge, Con Ed does not operate a Peterson grounded or a high impedance grounded distribution system.
Fair enough. And another participant asked, so the reclosing sequence that they had seen was breaker opens, 0.3 seconds, the breaker closes, it opens again. This is for a bolted fault. Then 3 seconds, it closes, and then we'll open the lockout. They were asking, what is the auto reclose sequence in North America? And I've seen on the breakers out of a substation, I've seen like a 2 second and then maybe a longer 5 second, and kind of doing away with the 0.3 that on a distribution line, that short or that quick reclose really doesn't buy you anything. So I've seen
That's correct. Yeah, I've seen
I just wanted to throw this out for your, put in your experience.
Yeah, it's the same thing. Mostly where I see the high speed clearing, which high speed we're talking about, a couple of hundred milliseconds to less than, a couple hundred milliseconds, where is on the transmission system, not so much on the distribution system. The high speed I've seen at the recloser in the and I don't know, what you consider high speed, but we're still talking about like maybe a second or so. So I've seen it out in the pole top recloser, where sometimes what happens is there can be an issue, and this we ran into when I was working at Con Ed, where if you have a feeder, because it's Manhattan, Brooklyn, Queens, a portion of the feeder is always going to be underground. And we know for underground faults are permanent in nature. There's usually nothing, no such thing as a temporary underground fault. It's usually the overhead. So usually the feeder, for example, in this comes out to the substation underground, it transitions to overhead to a pole top closure. So the problem is, because the feeder breaker is coordinating with that pole top reclosure, it becomes slow. So if we have a fault on the underground portion of that feeder, it can take a long time to clear. The problem we had was there's feeders share manhole. So multiple feeders in a single manhole. You have somebody working in a manhole on a different feeder, and that feeder adjacent faults in that same manhole, and it doesn't get cleared fairly quickly. That's a dangerous condition for that person in the manhole. The copper melts, the insulation melts, it can cause dangerous toxic fumes apart from the arc flash issues. So it's a dangerous condition. So what we ended up doing was we set the recloser had a high speed curve. So we set the recloser on a high speed curve. And we set the relay to coordinate with that high speed curve so that the relay will trip faster so it does not have to coordinate with the slow speed curve of the recloser. The problem happens is if the recloser does operate on the high speed curve and it closes back in, the recloser now switches to a slow curve. Now, if the feeder relay is still on the high speed curve, when that recloser relay closes back in its slow curve, it's going to trip. Again, not the desirable situation. So we had to develop some special, and this is where microprocessor relay helps a lot. We had to develop a special logic so the relay switches to a slow speed curve when it sees the auto recloser operate and reclose back in. So that's a very special situation with that. I think I kind of beat around the bush with that question a bit, but the bottom line is I've seen the high speed on transmission, not so much in distribution. Auto reclosing. If we have no other questions, Paul, I have a couple other questions here. What are some applications using Goose messaging for feeder protection? So I kind of talked about them briefly, but I didn't mention that Goose messaging could be used for them. So one of them is the auto reclosing scheme. So instead of having, again, these coordinating effect where I need to coordinate the auto recloser to the downstream ones, I can use the communications to do coordination where I could send that blocking signal back either to the substation, then the substation sends that signal to the relays on the pole. And I can do that with IEC61850 Goose messaging. However, for an auto reclose for pole top relay, what is the communication that I need to use? Obviously, I can't directly wire it because those poles might be miles away from the substation. So the typical scheme is to use wireless radios, GE's MDS radios, Orbit radios. And we actually, in this cabinet here, if I spin it around, I don't have a picture of spinning it around, there's an MDS radio in this cabinet also to be able to communicate, make that communication back. So We can use IC 61850 to do some sort of recloser, automatic coordination, auto reclose schemes. Say we have a fault out in the feeder, we can bring all that information back, determining where the fault is, and then switch around that fault automatically. So a lot of intelligence we can do that with. The other one was the zone interlocking I talked about. I could find it. Can't find it right now. Oh, the zone interlocking. So I talked about sending that blocking signal again. So we could use fiber optic and we could use Goose messaging for that. Go ahead, Paul. Sorry. Did you try to say something, Paul?
No, that wasn't me.
Sorry.
Okay, sorry.
Mike, you may also want to mention a main time main scheme using 61850.
I don't have that example here, but yeah, Eduardo is right that we can use a main scheme. I was looking for it here, but I couldn't find it in my slide. That's something I did miss. So you could, instead of when you have the main time main, you have a feeder on the main, two main breakers, and you have a feeder, not a feeder. You have a relay on the two main breakers, and you have a relay on the tie breaker. Depending how you want to operate your scheme, if you lose one of the utility source, you can close that tiebreaker in to energize your load. And typical is you need to know, the status of the sources, and you need to know the status of the main and the voltage sources. So what you typically would do, you'd wire contacts between those relays, and it could be like 7 or 8 contacts that you have to wire. So you can replace all of those contact wiring with IC 61850 Goose messaging. The beauty of it is you just have to run one, fiber optic cable, maybe a switch to be able to do that, and you eliminate all the wire pulling that you have to do, wire termination, wire testing that you have to do. The communication scheme, any communication scheme, is constantly monitored. Right? It's constantly monitored in real time. So if there's a problem in the comm scheme, you get an alarm in the relay right away. If there's a break in the wire in the field, if you had a wiring scheme, you had a break in the wiring in the field, you wouldn't know about it until something happens, right? You call upon for a main scheme to operate, to switch the tiebreaker in, and it didn't, because you had a break somewhere in the wiring, and you didn't know about it until it was too late. With a comm scheme, it's constantly monitored, and you'll know about any issues right away. Any other questions there, Paul? Another question.
Now you go ahead. I've been just having my own little conversation here with everybody. So. Okay.
So one of the questions: what are some what components that need to be considered when we're determining coordination time? So that's a good question. I mentioned 0.3 to 0.4 seconds, but I never really mentioned what went into that. And so basically, obviously the time the relay takes to operate, close the contact, the time the breaker takes to open, so whether it's a 4-cycle breaker, a 5-cycle breaker, and some safety margin. So typically when I said 0.3 to 0.4 seconds, usually if you're coordinating microprocessor to microprocessor relay, then you can go on the low side. You can go on the 0.3 because that microprocessor relay, especially if the same manufacturer and the same model, they basically act exactly the same way. It's just a calculation that they're doing internally. They're gonna act the same way. So you can be a little more close with the coordination time. However, electromechanical, you coordinating electromechanical to microprocessor or electromechanical to electromechanical, there's a little more uncertainty on, depend who calibrated the device, how well is it calibrated, the overtravel time of the disk and such. So in that, you want to give yourself a little more margin for the coordination time. So that's why we set it about 0.4 seconds. And with that, Eduardo, I'll push it over to you to close the call. We're right on the 4 o'clock mark.
Thank you, Mike, for a very excellent, oh, I would say an excellent presentation, and Paul for answering all the questions that were coming in. I would like to thank each and every one of you that took the time to participate in today's session. Hopefully, it was educational and productive to all of you. Like I said at the beginning, we'll email you a copy of the presentation for your records. And if you need a certificate for the participation and the hours, please email Team Fahey or myself, and we'll make sure to get it out to you really fast. With that, I just hope that everybody has a great afternoon, and we end this session. Thank you.
Thank you.